This is Coker presenting my final project for CS231A on reflection recovery and removal in photographs. Reflections are very common, and depending on the application, they may be a nuisance you want to remove or an interesting signal to extract. Previous work falls into several categories. Physical solutions like polarized lenses are not acceptable for everyday use of mobile phones, and separating the reflection from the background in a single image is an ill-posed problem. The approach I'll discuss falls into the last category of multiple view recovery, where several images are combined to separate the background and reflection. Existing approaches use such techniques as optical flow, which assume that each layer is opaque, and can't deal with combined background reflection pixels, which are a composition of two layers. I explored a recently proposed idea called edge flow. My main contribution has been implementing everything from scratch, which required algorithm design decisions when the literature had gaps. I also filled in some holes in the optimization derivations and thought of novel constraints that I hope to test. The key observation of edge flow is that edges typically belong to either the background or the reflection, but not both, since that would require the edges lining up perfectly between layers. Also, due to the scene geometry and the usually different depths of the background versus reflections, those layers move differently between views, so we can exploit parallax differences to separate the layers. The purpose of edge flow is to provide good initial estimates of the background and reflection layers, and of the background and reflection motion fields, which then go into a nonlinear optimization problem. So, how does this process work? A reference image is chosen from a series of images taken from different views. The index T image can be written as a vector and decomposed as a sum of warped versions of the reflection and background components of the reference image. The warping matrix W is an n pixels by n pixels sparse matrix of interpolation weights, and there is a different warping matrix for the background and reflection layers because they move differently. The motion field for the reference image is all zeros, and its warping matrix is the identity matrix. The alpha mat is a constant between 0 and 1 that describes the relative contributions of the background and reflection components. The motion field between images is found by calculating the normalized cross-correlation for a window around a canny edge pixel to all areas in the second image. After determining peak centroids, the coordinate offset gives the relative motion for that pixel between images. Doing this for each canny edge pixel gives a sparse motion field. Some spurious matches are seen here. Next, I assumed that the background dominates, so edge pixels are more likely from the background. I used Ransack to fit a projective transformation to background pixel inliers. Then the remaining pixels must be reflection edge pixels or noise, so Ransack fits another homography to the reflection pixels. There are now separate sparse motion fields for the background and reflection. Next, I interpolated the sparse motion fields to get dense motion fields defined at every pixel. Each image is warped according to its dense background motion field so that all images are aligned to the reference image. Cycling through images, the background is almost completely stationary while the reflection layer slides over it. This shows how the reflection and background layers have been decoupled. Because the background and reflection components are assumed to be additive, we get an initial estimate of the background image at each pixel by taking the minimum value for that pixel over the image stack. There are still some obvious reflection components in this background estimate, for example the blue monitor at the top left, but some of the reflection is successfully removed. Remember, this is just the initial estimate. Similarly, the reflection is calculated as the pixel-wise reference image minus the estimated background image. For visibility, I've adjusted the contrast of the previous image. You can see interesting features of the reflection, like the coffee mugs and the letters on the board, which were indiscernible in the original input image. Everything so far was to get good initial values for this large nonlinear optimization problem. We need to minimize the difference between each image and the warped background and reflection layers. Alpha and all the pixel values are bounded between 0 and 1, and other constraints have been shown to help. I personally think that it might be interesting to impose constraints on the divergence and curl of the motion fields. The optimization can be done in a two-step alternating procedure where first the motion fields are held constant and the pixel values optimized, and then the pixel values held constant and the motion fields optimized. So that's how it works, and here are some references.